Ever wondered how a roller coaster can send you upside down at incredible speeds, twist through impossible angles, and still stay perfectly locked to the track? Today on Knowledge Hub, we're diving deeper into the physics, engineering, and hidden technologies that make roller coasters feel like they're defying gravity. It all begins with energy. When a coaster is pulled up the first massive hill using a chain lift system, a motor drives a chain that engages with a hook under the train, slowly dragging it upward. In modern launch coasters, systems like linear induction motors use electromagnetic fields to accelerate the train instantly without a chain. Either way, the goal is the same: to store gravitational potential energy. The higher the train climbs, the more energy it stores. This is calculated using MGH, where mass, gravity, and height all play a role. And the moment it reaches the peak, everything changes. As the train drops, that stored potential energy rapidly converts into kinetic energy, increasing velocity dramatically. This is why the first drop delivers the highest speeds, sometimes exceeding 150 kilometers per hour. From this point onward, the coaster becomes a perfect demonstration of energy conservation, constantly exchanging potential and kinetic energy. Now let's talk about what really makes it look like gravity is being broken: loops and inversions. When the coaster enters a loop, it needs to maintain a minimum speed at the top to avoid falling. This is achieved through centripetal force, where the motion of the train creates an inward force toward the center of the loop. At the top, the train is moving so fast that centripetal acceleration keeps you pressed into your seat and the track. But early roller coasters used circular loops, which created dangerously high g-forces. That's why modern coasters use clothoid loops, wider at the bottom and tighter at the top. This gradually changes the radius of curvature, distributing forces more safely across your body and preventing excessive strain. Speaking of staying on the track, roller coasters don't just sit on rails. They are locked onto them using a trike-wheel assembly. Each train has road wheels on top, side friction wheels for lateral movement, and upstop wheels underneath to prevent lifting off. This design is what allows coasters to safely go upside down without any risk of detachment. Now let's dive into the forces you actually feel. These are called g-forces, and they're carefully controlled. Positive g-forces push you down into your seat, up to 5 times your weight, while negative g-forces create that floating airtime sensation. Engineers design camelback hills to maximize this effect safely. Another factor is energy loss. Friction between the wheels and track, and air resistance, continuously drains energy from the system. This is why no point after the first drop is higher than the starting hill. Engineers simulate this to ensure the train completes the track. Modern roller coasters use block section systems, dividing the track into segments where only one train can occupy a section at a time. And when it's time to stop, magnetic braking systems take over. These brakes use eddy currents to slow the train without physical contact. Materials also play a huge role. Tracks are made from high-strength steel, fabricated to handle repeated stress cycles, temperature changes, and dynamic loads. So the next time you're hanging upside down on a roller coaster, remember, it's not defying gravity at all. It's using gravity, motion, and perfectly calculated forces to create one of the most thrilling experiences possible. If you have enjoyed this deep dive into how roller coasters defy gravity, don't forget to subscribe to Knowledge Hub for more mind-blowing explanations. And as always, stay curious.